Recorded Detail and Distortion, Chapter 28 and 29. Recorded Detail. Assessing recorded detail. Geometric properties of image quality are both recorded detail and distortion. Recorded detail is the degree of geometric sharpness in the image, aka also known as definition, sharpness, spatial resolution, or detail. Assessing recorded detail continued. Digital imaging systems. We talk about it as spatial resolution, and it's dependent on the matrix size, pixel size, and grayscale bit depth. Unit of resolution. Line pairs per millimeter is our measurement. We use a resolution test tool. 28-1 in your book is an example of that. For clinical evaluation, we use a tabular pattern. Smaller structures, easiest to examine, and we're looking at bony trabecula. It's a guide post to image resolution. Assessing recorded detail continued. It's a lack of detail, unsharpness, and can be created from penumbra. So these are examples of, to your left, of good resolution compared to your right, which is fair resolution, but it would be poor if considering for the femur. So these are the things that we're going to talk about: spatial resolution, spatial frequency, point spread function, line spread function, modulation transfer function, and noise. Spatial resolution, ability of imaging system to accurately display objects in 2 dimensions. So it's higher when 2 objects can be demonstrated smaller or closer together. Digital is 3 dimensions of the image, which is x-axis, y, and z, which can be used in like CT and MRI. Together they express quality of spatial resolution. This is an example, and you can use the YouTube video below to describe spatial resolution in grayscale. So you can see the z-axis is the bit depth in the pixel, or the grayscale, and is considered a voxel or 1 pixel. X plus y equals the spatial resolution. PSF, LSF, and ESF, measures of spatial resolution. So point spread function, line spread function, edge spread function. Table 28-1 in your book helps explain these. Edge spread ESF, express boundaries of an image, measures penumbra or blur, and is expressed in Point mode by drilling tiny hole in the sheet of lead and imaging it. You get with a point stimulus. This creates a point when it intersects with the imaging plane and responds isotropically. And then B is a 3D graphic of the image receptor response to the point. X-ray imaging a point by drilling that tiny hole in the sheet of lead and then producing an image of the hole. Nuclear medicine, point source of radioactivity. CT, you use a thin metal wire. Sonography, monofilament. In MRI, a small water hole in tissue equivalent phantom. Spatial frequency, a shorter wavelength signal, high frequency signal, high resolution, a longer wavelength, low frequency, low resolution. It's determined by measuring distance between pairs of lines distinct from one another. The higher the frequency, the closer the sine waves, the closer the line pairs. Modulation transfer function. It's the percent of an object contrast that is recorded by MTF. So measures accuracy of an image to the actual object, aka fidelity or its trueness. At 0, there's no signal, no image. At 1, it becomes a perfect image. So 1 line pairs per centimeter. 3.0 drops the MTF. So again, it's a scale really from 0 to 1 and plotted to size of the object. Noise is blotchy or has a molted appearance. It is background information received by the image receptor. Quantum noise, aka quantum model, is a lack of sufficient incoming data. Quantum means actually counted or measured. So this is just showing you when noise rises, more complex processing logarithms may be necessary when we meet limit degradation of the image. Solution is increase the signal or increase mass to control or fix quantum model. And this is just showing you the effective exposure of image quality and showing you high noise with low exposure and so forth. Digital sampling, the Nyquist criterion. So signal average over the detector aperture width. So digital systems sample discrete points. The frequency signal point may be sampled twice per cycle. So A equals the high frequency digital signal, and B is a violation of the Nyquist and law frequency signal, or AKA called aliasing. I encourage you to watch the YouTube video posted here that will help you see the Nyquist criterion. Aliasing, or the Moiré effect, occurs when the Nyquist criterion is not met. Low frequency image wraps around the high frequency image. Visual appearance of two images slightly out of alignment in a Moiré pattern. Mistaken for grid error quite a bit, but it's not. It's only found in digital systems that don't completely read the image correctly. And again, another video is provided for you so that you can see what aliasing and how this actually occurs. Effects on image appearance. Images lacking fine detail appear blurry, and it's an assessment of motion. So it's better with clinical experience. The more you see, the better you get at visualizing motion. So this one right here, this image, if you kind of look at the abdomen, you can really see the blurriness to it. And it is an image of motion, or what we say is unsharp. Factors affecting recorded detail. Eliminate motion, reduce OID, reduce the focal spot size, reduce intensifying screen phosphor size and concentration, and increase SID. Geometry. Most important level of resolution for recorded detail. So distance, SID, and OID. And this is due to the focal spot size. So this image is showing you at point B, it has more than what point A would have. Distance. Resolution improves with OID decreasing and SID increasing, which is something that we've taught from the very beginning. We want them as close as we can to the IR with least amount of space in between, and we always use a longer SID of at least 40, if not the 72. OID should be kept to a minimum. Tabletop to Bucky tray distance. Non-Bucky decreases OID. An example is of like your lateral C-spine done at 72 inches instead of like 40 inches. This is showing you the differences in image quality. The image to your left is 7 centimeters with OID. The image to your right is a 14 OID. Both are at 80 kVp and both are at a 10 mass. Focal spot size is controlled by line focus principle. Umbra, distinctly sharp area of a shadow. Penumbra is the imperfect, unsharp shadow surrounding the umbra. So penumbra is equal to the focal spot size times the OID divided by the SOD. Digital is measured through either PSFs or the LSF. Example, and again, this will be on your test. Calculate the penumbra for an image taken with a 2 mm focal spot at 40-inch SID distance and an OID of 2. So 2 times 2 equals 4. SOD minus the OID, which equals 38, would equals to 0.105 millimeters. Attenuation, absorption of sharpness. Penumbra is increased because of this attenuation or unsharpness. Penumbra is due to the divergence of the beam, and as we look at this example, you can see how the trapezoid has still really sharp edges. The square has density shading because of increased attenuation, and then the circle has varying density, gradual images, and it has no really sharp edges to it. Digital image receptor systems. So CR imaging plates, they are classified by their speed. Limitations are similar to intensifying screen. Phosphor size, phosphor layer thickness, and phosphor concentration. Also affected by IRD or the image reader device. It's dependent on the phosphor size layer, thickness, and concentration. Size of the detector element primary limitation. With indirect DR, flat panel systems, screen, CCD combo, Limitations are similar to the intensifying screen. With silicone, scintillator, or TFT combinations, we end up with a fill factor that is an area of detector that is light sensitive. A high fill factor equals high resolution. Digital image receptor systems continued. Size of the detector element primary limitation. Direct DR or flat panel selenium systems image processing system limits recorded detail. It's dependent on the acquisition and display matrix, pixel size, grayscale bit depth. Motion, voluntary motion, we know is best avoided with great communication, which we've talked about from day one. Involuntary motion, reduced exposure time, and possibly immobilization. Equipment motion can be really hard to detect to see that if it's the patient or if it's the equipment itself. Again, best to reduce motion voluntarily is through effective communication. The technologist must establish an atmosphere and be professional and competent. Involuntary is not controlled always by the patient. It's best reduced, again, through short exposure times. Immobilization, when communication and time are not enough, tape's an easy one that you can use. As last resort, you can use others to hold the patient down, like x-ray techs. Should be actually the last choice. You should use somebody else, because again, we're in this almost every day. And heartbeat and peristalsis are really the most common types of involuntary motion. Chapter 29, Distortion. Assessing distortion. Geometric property of image quality, it controls detail. Definition of distortion, misrepresentation of size or shape of structures. So there's really two types that we can see, size or shape. It always exists when contrast and density are poor, even if you cannot see it. It can only be minimized. You must know about shapes of anatomy to best possibly image. We want images to actually look like the real thing. Factors affecting distortion. This is a great chart that kind of divides it up. It shows you that, if it's size, it breaks it up into OID, SID, shape, and the other controlling factors. So you might decide you want to study from this. And again, this is just distortion is directly related to positioning. So it's either going to be size, shape, distance, or tube, and then how we minimize the distortion. Factors affecting size distortion. Film, only magnification. Minification, impossible due to divergence. Radiographic distances. SID maximize, OID minimize. Digital systems, magnification and minification are possible due to post-processing parameters. It's reduced magnification, size distortion, increase resolution of recorded detail. Exception found in magnification radiography, where you want the images to be large. Source to image receptor, or SID. The greater the SID, the smaller the magnification. OI decreases with critical for magnification and resolution. 40-inch, not always the norm. Back in the 1918s, it used to be 20, and it increased in 28 to 25 to 36 inches. It had to be that way because the tube could not handle the load. Finally, in 1945, it was established that 40 would be used, and now some use more or less. Most are kind of increasing to like 48 as the minimum, kind of due to the same reasons. SOD is included in SID divided by the OID. Maximize SID, decrease magnification, and that's why 72 inches is used for like chest x-rays and lateral C-spines. SOD plus OID equals SID. Source to image receptor distance, or SID. This is just showing you the effective SID on size, on image size. OID, it's critical with magnification and resolution. Perceptions are reversed for radiography. Further an object from a receptor, the more you have with magnification. It's opposite of how we see things. Normally it will look smaller the further away it is. This is just showing you the effective OID on size magnification. So A and B are the same size, but images show up differently. And C is smaller, but the images are identical because of the OID. Knowledge of anatomy is a must to judge size relationships. OID varies with position and part size. So this is why two projections are always needed of 90 degrees from each other. So we always have an APN lateral because it is hard to judge size relationships. OID is in dosimetry, establishes source to skin distance, accounts for increased exposure. Larger patients receive greater dose because skin dose is more, making the SOD less. Again, they're just closer to the tube. Minimize OID, you decrease magnification. Calculating size distortion. Yes, it's going to be on the test. So size distortion is measured by simple geometry. Magnification factor is equal to the SID divided by the SOD. So here's an example. The SID is 40 and the SOD is 15. What is the magnification factor? So again, just kind of plug it in. 40 divided by 15, it equals 2.667. Image will be 267% of the object size. Again, another formula that you need to know is SID equals the SOD plus the OID. Again, another calculating object size. So this one is O equals the I, where I is the image size, divided by the magnification factor. Example, if a projected image measures 3 inches and the magnification factor is 1.33, what is the size of the actual object? Again, play it out, and you end up with an object size of 2.25. Remember other formulas that could apply. If image size and object size are known, the percent of magnification can be determined by I minus O divided by O times 100 equals the percent of magnification of an object. So objects smaller than the effective focal spot, they cannot be demonstrated unless modified for its width. Factors affecting shape distortion. Definition: misrepresentation by unequal magnification of the actual shape of the structure. Elongation, just like it sounds, is longer than it is. When the tube or image receptor are improperly aligned, so it's due to tube angle. Foreshortening is when it's shorter than it is, and when the part is improperly aligned. Changes in tube angle can cause elongation, never foreshortening. So it's caused by structures that lie on a different level in the body, divergence of the beam, lengths may vary depending on angle and part of the beam. Adjustments, consider beam-part relationship. So other factors affecting shape distortion are alignment and angulation. So this is going to be alignment, which is central ray, anatomical part, or image receptor, or angulation, which is degree and direction. Alignment can cause or avoid shape distortion due to poor or proper positioning of the tube. Central ray should be at right angles to part and image receptor, so they should be parallel. Central ray should be perpendicular to the part and image receptor. Sometimes you must get creative to actually obtain the images that you desire. Incorrect centering result from off-centering tube, incorrect positioning of part, or off-centering receptor. Central alignment. This is just showing you shape distortion due to the angle between the object and the beam. This is an example of incorrect centering and how it'll affect your image. Central ray. Theoretical photon that exits from center of the focal spot. Perpendicular to part and image receptor. If not central ray, it will be distorted. So the further from the central ray, the greater the distortion. It's important to be accurate. Think of like long bone structures or studies. Has anyone ever measured or looked for links? What if you were off? What if you had some type of central ray angulation that would make those links differ and might have them shave part of that leg that shouldn't be? Centering away from central ray point, same as angling the tube, and creates distortion. When the part is superimposed over structures, the central ray angle is useful. Failure to maintain correct relationship between part and receptor may produce a useless image. Anatomical part. Normally positioned with long axis perpendicular to the central ray and parallel to the receptor. Some projections used to avoid superimposition. Failure to maintain relationship may result in a limited value image. 29-11 is a good reference. It looks at both foreshortening and elongation. Image receptor, perpendicular to the central ray, parallel to the part, off-centering only caused by clipping anatomy. It results in a repeat or no distortion. So if the image receptor is plane, on the same plane, if not parallel or centered, distortion will occur. The relationship must maintain for a useful image. Angulation. Direction and degree tube is moved from normal position to image receptor. It can be used to avoid superimposition, some shape distortion expected. Also causes changes in SID. If not, compensated for causes a decrease in exposure. Direction. Longitudinal angulations. So we know cephalid means towards the head, and caudid means towards the feet. Transverse is right or left, and the direction of the tube angle is identified or specified to position and must be maintained. Degree is defined as the exact amount of angulation, as angle between central ray and receptor plane from reference point of perpendicularity. So standard point is 90 degrees angle, must be added or subtracted from this point. You must maintain correct angle. Tube angulations change SID, which changes magnification. Evaluating shape distortion. Effect cannot be calculated. It's subjective evaluation and requires knowledge of normal anatomy and projections. Size, a matter of magnification. All magnification results in loss of resolution. Shape, again, elongation and foreshortening, in some instances can be used for an advantage. A helpful hint for the test is Table 29-2. Again, it just kind of breaks down how things affect distortion. And that is the end.